In this video, we're going to elaborate on the two different ways that we've developed of creating a simple extension of a field. So for example, suppose we have the rationals, and we want to think about adjoining the square root of 2. We now have two different ways of approaching that. The first way of constructing this is to take the polynomial ring over the rationals and take the quotient by the ideal generated by x squared minus 2, which is an irreducible polynomial having square root of 2 as a root. So we claimed before, and we showed this, that this is an extension field of the rationals, and it contains a root of the polynomial x squared minus 2. So that's one way. Here's the other way. So the second way is to envision some extension field of the rationals which is big enough to contain the square root of 2. So for example, we know about the reals. I'll just say consider a larger field, and the one that we'll use is R. And take the smallest subfield containing the rationals, which actually any subfield of the reals will contain the rationals because the rationals are the prime field. You can't have a field here without having all of the rationals. And the square root of 2. So take the smallest subfield containing the rationals and the square root of 2. So you picture all the real numbers and then think, okay, what if I have all the rationals and I have the square root of 2, exactly which elements do I need to have in my field? And the happy result is that both of these methods lead us to the same place. Both of these methods will lead us to a field with elements of the form a plus b square root of 2, whatever we're calling the square root of 2, whether it's actual square root of 2 from the reals or this mysterious x which satisfies the equation x squared minus 2 equals 0, a plus b root 2, where a and b are rational numbers. Both of these will lead us to that point. But in this video we need to show that that works in general. That is, if we extend a field by taking a quotient by an irreducible polynomial, or extend a field by just adjoining a root, just tacking one on from an extension field that we know is big enough to contain it, both of those methods give us isomorphic fields. So here's the theorem that we're going to prove. Theorem, let F be a field, and let P of x be an irreducible polynomial in F adjoin x, so it's irreducible over F. Okay, and also let K be an extension field of F that contains U, a root of P of x. Okay, so F is a field, we have an irreducible polynomial, so assuming that its degree is greater than 1, it's not going to have any roots in F, but it does have a root somewhere, and we're going to call that somewhere K, an extension field of F that contains a root of this polynomial. All right, that's not the theorem, that's just the setup. So now the theorem is, then, this field, which I obtained by taking a quotient of F adjoin x with the irreducible polynomial P of x, that's isomorphic to F adjoin U. We're going to prove that those are isomorphic. And this is a wonderful theorem because this is an opportunity for us to pull out the first isomorphism theorem and actually use it as a tool to prove that a quotient ring is isomorphic to something. And if you take nothing else away from this video, which I hope you will take other things away, don't get me wrong, but if you take nothing else away, I think the main thing that I want you to take away from this video is if you're trying to understand the structure of a quotient ring and show it's isomorphic to something more familiar like this, then the first isomorphism theorem is a great way to start. It's a great place to try to start finding an isomorphism between your two rings or your two fields. So take that away if nothing else. All right, so here's how the game's going to work. We're going to try to use the first isomorphism theorem, meaning that we're going to build a homomorphism from F adjoin x to, well, not exactly F adjoin U, although it will end up being a homomorphism into F adjoin U, but we're going to just start by defining a homomorphism into K, because what we're going to define will definitely be a homomorphism into K. And we will show two things. Well, first we need to show it's a homomorphism, but that's actually going to be a result of something we've already proven. We're going to show that the kernel of that map is the ideal generated by P of x, we're going to show that the image of the map is only the smallest field containing both F and U. All right, so let's begin. The homomorphism we're going to use actually is not one totally unfamiliar to you. You've seen this one before. We're going to consider the evaluation homomorphism called phi sub u from F adjoint X into K. Okay, now we've seen evaluation homomorphisms from F adjoint X into F. I think we briefly touched on evaluation homomorphisms into a bigger field, but we need to map into a bigger field this time because we're evaluating each polynomial not in an element of F, but at U, which does not belong to F, it belongs to K. All right, so we're going to use this evaluation homomorphism. We're going to analyze its kernel and its image. Okay, we know this is a homomorphism. Already. I don't know if we gave a formal proof, but if you wanted to give a formal proof, here's what you would do. You would suppose that you have two polynomials here and show that evaluating those two polynomials at U and then adding the results gives the same answer as if you added the polynomials together and then evaluated the resulting polynomial at U, which I realize that's a mouthful, but if you think about that statement and kind of wrap your head around what it's saying, it does seem kind of clear that that's how things would work. Like evaluating and then adding should give the same result as adding polynomials and then evaluating, and same with multiplying. So we're not going to belabor that proof here. It would make this video 30 minutes long because it's really just formalism after that. So we know this is a homomorphism. So now we want to think about its kernel and its image. So first of all, what is the kernel of phi sub u? What is the kernel of that map? Well, first of all, it's the set of all polynomials, and I'll call these lowercase f of x, belonging to f adjoint x, such that f of u equals 0. And there's at least one polynomial that we know is in the kernel. Well, we know the 0 polynomial is in there, but that's not that interesting. There's an interesting polynomial that we know is in the kernel, and that is this p of x, because what was u? We defined u to be a root of p of x. So we know p of x belongs to the kernel of this map. Okay, so that's great. And just keep in mind, I would like to show that the kernel of this map is exactly this ideal, the ideal generated by p of x. Okay, we want to show the kernel of the map, phi sub u, is exactly this ideal. All right, so I'm going to start trying to prove this using my usual approach, which is I want to prove two sets are equal, prove each one as a subset of the other one. I'm going to start by proving this one is a subset of the kernel because I think that is likely to be easier. So what do we know? We know that since p of x belongs to the kernel, the ideal generated by it also has to belong to, or has to be contained in, the kernel of this map. Okay, wait, why is that true? Well, we know that this consists of all of the multiples of p of x. And if p of x belongs to the kernel, that means p of u is 0. I take any polynomial that's a multiple of p of x, evaluating that at u is also going to give me 0. Okay, another way of viewing it is to say, well, look, we know that the kernel is an ideal, so it has to absorb multiplication. So in particular, it has to absorb every multiple of p of x since it already contains p of x. That's another way of getting to the same place. Okay, so I know that. But proving the other inclusion, proving that the kernel is contained inside of this ideal, is a little bit harder. And the way I'm going to close that loop is by doing something a little sneaky here. Just an observation. Because p of x is irreducible, because it's irreducible, I know the ideal generated by it is maximal. Okay, so I know that that ideal is maximal, and I know that the kernel is an ideal that contains that maximal ideal, and it sits inside of the domain of my homomorphism sits inside of f adjoint x. Okay, so this is a maximal ideal of f adjoint x, and I know that the kernel of this map sits somewhere in between those. Well, if you sit between a maximal ideal and the entire ring, you're either that ideal or you're the entire ring. And I'm going to show that you can't be, the kernel can't be the entire ring. We know the kernel is not equal to all of f adjoint x because, for one thing, this polynomial belongs to f adjoint x, and that polynomial is most definitely not in the kernel of the evaluation map because that is the polynomial 1 is a polynomial which, when evaluated at u, does not give 0. It is not going to, there's no way. So that should be not included in. There we go. So 1 does not belong to the kernel. So I know that the kernel isn't the entire ring, but it contains a maximal ideal. That means it has to be the same as the maximal ideal. So since this is maximal and a subset of the kernel, which is also an ideal, the kernel of phi sub u, sorry, hungry cat in the background, the kernel of phi sub u is equal to this ideal. That's exactly what we wanted to show. So now I know about the kernel of this map, the evaluation homomorphism. Now we need to think about the image. So here's what the next phase of the proof looks like. Let me keep the main result in the window here so we can see it. All right, so next up, here's what we need to do. We need to show that the image of the map, the image of phi sub u, is exactly the field f adjoin u. That is, it's the smallest subfield of K that contains both f and u. Now, we do know that the image of this map, the evaluation map, is going to be some subring of K. We know that because when we evaluate a polynomial at u, well, our polynomial has coefficients in f, and those all belong to K. And we're evaluating at u, so we're possibly multiplying and adding powers of u, and those also belong to K. So all the calculations that we're doing belong to the field K. They sit inside of that field. So we know that the image, whatever it is, will be some subring of K. But we need to go a little bit further. We need to show it's a subfield, and we need to show it's the smallest subfield containing f and u. So first let's deal with why the image of this map is a field at all. We know it's a subring of K, but why a subfield? All right, so let's see if we can prove that. So why is the image of phi sub u a subfield of K? Well, in thinking about that, it might be tempting to try and show that the image contains all of its multiplicative inverses for non-zero elements, but I'm actually going to do something a lot sneakier here. I'm just going to say we know by the first isomorphism theorem that the image of this map, the image of phi sub u, is isomorphic to the polynomial ring f of x mod the ideal generated by p of x. And because that ideal is maximal, generated by an irreducible, we know that that quotient ring is a field. Well, if that's a field, then the image has to be a field as well. So that's how we know that the image is a field. All right, so let's write that down. So the image of the evaluation map is a field. And we also know that it contains every element of f and also contains u. Why is that? We also know that this evaluation map maps the polynomial x to u, and it also maps every element of f to itself, because every element of f can be treated as a polynomial. So for every a and f, we can think of A as being in f bracket x, and that element, that polynomial, maps to the field element A under phi sub u. Okay, so the image of phi sub u contains f and u. So the image of this map, just to summarize what we know so far, is a subfield of K containing f and u. But why is it the smallest? Well, to show that the image of this is the smallest subfield containing f and u, I'm going to show that any other subfield that contains f and u also has to contain this entire image. So let's suppose H is also a subfield of K containing f and u. Okay, so just to give a visual diagram of what we're going to do here. So here's our field K. This is the big field that contains u. And then here's our subfield f. Okay, so the goal is going to be to show that if u is here, remember u is an element not belonging to f, and this is the image of my map, phi sub u, then if I have any other field, H, which is a subfield of K containing both f and u, it has to at least contain everything in the image of the evaluation map. So that's the game plan. All right. So suppose that T is an element of the image of phi sub u. All right, well then T has to be the image of some polynomial in f adjoint x after we've evaluated that at u. So then T has to be, well, so basically a polynomial with coefficients in f and a polynomial in u. So it has to be equal to a0 plus a1 u, etc. up through am u to the m for some coefficients a0 through am belonging to f. Okay, so that's a typical element of the image of the evaluation map. But we know that everything here is obtained by just multiplying various things from f and various powers of u. And all of those things belong to H. So we know, since H is a field containing a0 through am and u, that means that T has to belong to H. So the image of the map, the image of our evaluation map, has to be a subset of H, in fact a subfield of H. So this means that the image of the map really is the smallest subfield of K that contains both f and u. It's the smallest subfield of K containing f and u, and therefore, well, what do we call the smallest subfield of K containing f and u? That's f adjoin u. All right, so now we've shown that the image of our map is the simple extension f adjoin u. And so we can say by the first isomorphism theorem, let's zoom out so we catch all of this. That's great. All right, so to summarize what we've learned here, in summary, let's go back to black for this. That's A there. By the first isomorphism theorem, f adjoin x, the domain of this map, modded out by the kernel of the map, the ideal generated by p of x, which by the way was a maximal ideal, therefore this quotient is a field. This is isomorphic to the image of the map, which is f adjoin u. So now we know that these two different methods for constructing a field extension are actually algebraically equivalent. They yield isomorphic fields.